He's spoken at this conference. He always has a tremendous amount of information. He's able to pack a little bit of it into the time we have, and it's just awesome to learn from him. He's been in energy research for about 12 years as a professional physicist. In 2000, he founded the Berlin Research Institute for New Energy Technologies, and he's also been president for the past 3 years of the German Space Power Association. So let's welcome Dr. Thorsten Ludwig.
Thank you. Okay. Can you, is it working? Good. So thank you very much. Also, thanks a lot to the organizers of the conference for giving me a chance to speak to you here. It's a pleasure being here. I hope you enjoy the presentation. So let's see, we need this. So this time, as you can see from the title, which was printed in the program, I will be talking about something fairly new, which came up last year in Europe, and that is the excess heat from this hydrogen tube, especially from the GEET, which is called the Global Institute for New Energy Technologies, which was founded by Mr. Moller, who is a Danish person currently living in the Czechoslovakia, and he has his research institute in Paris. So, and we met him, and I will show you a picture of our visit to his lab, and I think he has some very interesting technology there. And so in this talk, we will first go through the foundation, which came actually from New York in about the 1920s. And yeah, we will see that it's quite related to the Brown's gas, so it's much earlier than the Brown's work. And Meyer and Brown, they have also shown technologies with water. So then we move on to the Moller story, which is linked to a story in Russia with a man called Frolov. I don't know if you've heard about him, but he has a research institute in St. Petersburg, and he brought out a very nice colored magazine for a couple of years called New Energy Technologies. Maybe some in English, maybe some of you have read that. I think he closed that down now because of it costs too much money to produce it. And then we move over to the GIFNet concept and the present work of Jean-Louis Nordin in Paris, which is one of the, you must have heard of Nordin. If not, you must visit his website. He's replicating like every new energy technology that you can ever hear of, including Tesla stuff and turbines and many other things, and lifters that we have seen here in Salt Lake also a couple of years ago. And well, then we move over to the last part of the talk, which is a little bit about physical explanation of why this is all easily possible. So this is Irving Langmuir, which is, he was born somewhere in the 1900s in New York and Brooklyn, and in 1909 he moved from an academic career into working for General Electric, and was working for them for many years in the research lab, and he was the one that actually made, one of the ones who really helped to get General Electric really big, because he solved some problems, and with these solutions they made a lot of money. And so he was working on filaments and gases. So at that time in 1909 they still had a lot of problems with the electric bulbs. They didn't last very long, and there were quite a few problems that they hadn't figured out. So he got started with that. And alongside of that, while you see at that time, most of the technical people, they tried to make the vacuum in the light bulb as good as possible, because they thought then the light bulb will last longest and will be brightest. So he got a different idea, because it was kind of difficult to get a better vacuum than they had at those times. So he got the idea, okay, I will try different gases and see how they react with a filament, and by that we can see if a better vacuum, we can achieve if we get a better vacuum. But let me finish this slide first here. So he also invented the atomic hydrogen welding process. We'll see some pictures of that. And he got the Nobel Prize for Chemistry in 1932.
Just a little bit here.
Okay.
Hold on.
Sorry about that.
Button your top button so we can.
Finished? Maybe I can talk while you finish it. Okay, so so you see, he got the Nobel Prize. He did quite some achievements in the chemistry. So in the reaction between gases and filaments, he really made some groundbreaking work. This is a picture of his hydrogen torch, which he invented, and it was widely used in the 1930s for special welding processes. It kind of works like this. Here the hydrogen comes in, and between these electrodes you create an arc, and you let the hydrogen flow through here, through the arc, and you create atomic hydrogen. So you separate the H2 into two hydrogen atoms, and you let this atomic gas flow to the point where you want the welding, and the recombination of the hydrogen and also the combination with the hydrogen and the metal creates a lot of heat exactly where you need it, so you can make very many special welding things. Little bit like what you can do today with Brown's gas. So this is like something which was used much before that, but it came out of use when they discovered other welding technologies like gases and inert gases and things like this. Then this kind of came out of fashion. So, so for us, his work with the gases and the filament is very important, because that leads to an energy anomaly, which is then also used in these hydrogen tubes today. So, so like I said before, they were working on lamps and trying to make them more efficient, and he was kind of, he could work the way he wanted, and what he did was not make a better vacuum like all the others. He filled all the gases he could think of one by one and studied how they react with tungsten filaments and what they do. And he found out that most gases, except water, they don't do anything to the filament, and then later we will see that actually it's much better to fill gas into the lamps, to have certain gas in it, and then you can make it much more efficient. So he became familiar with the effects of gases, and his idea was to extrapolate to zero gas pressure. So he studied also the hydrogen and found some very interesting results. So this is just his invention by which the General Electric company made their astronomical fortunes, because like at the end of, I think, 3 years of working with the gases, he found that the water which is on the glass when it's produced, that really makes the problem. And when you produce the lamp in such a way that there's no water inside the lamp, then it already lasts very long. So then you just fill in a few gases, and all of a sudden you have a lamp which lasts for 1,000 hours, which was much at that time, and you have 80 to 30% more efficiency. And with this invention, General Electric went on and became a big company. So that was really his invention. But as a side of on the side of this, he also worked with the hydrogen, and he found that with normal gases, you have like an energy loss or like an energy transfer to the gas with a square of the temperature. And that is also true for hydrogen. But when you reach something like nearly 2000 Kelvin, 1800, then all of a sudden you slowly become to an increase which goes with the fifth power. And that has much to do with the dissociation of hydrogen. But it doesn't dissociate fully, but even if you have a few percent of the atomic hydrogen, you get this effect already. And then he found this, and this is very important because it kind of contradicts what Niels Bohr calculated, and they were in touch. And so he found by actual experiments that the dissociation heat is like 130,000 calories, while it should only be 60,000. And it becomes more drastic when you read here what was once in the Encyclopedia of Science. And you can split the hydrogen with only 103 kilograms per gram, and you get out 90,000. So this energy anomaly, which is kind of lost, is some people, they have not lost this knowledge, so they made these hydrogen tubes from it. So basically, if you split the hydrogen and you recombine it, then you can get all these extra heat from it.
You said that's 90,000 calories.
Well, this is an experimental figure.
Not 90, it's 90,000, right?
Yeah, 90,000. Mm-hmm. So here you see the tube, and this tube, we will see the plans and how it's made in just a second. This was made in Russia, and so Nicholas Moller, who's the founder of the GIFnet, he went to Frolov. Now I have to say this is his side of the story, okay? So Moller says he went to Frolov and told him to build these, and now finally he has got them back. While Frolov says, well, it was mainly his idea, and Frolov then, you see, Moller has this nice idea of he wants to spread this knowledge as far as wide as possible, and he has the open source approach. So that means you can download the plans, and he's giving out all the knowledge of his tubes, and he thinks that the breakthrough will come not by hiding and not by trying to make it as secret as possible, but to make it very open so everyone can make it. The thing is, this tube is not easy to make. We will see the plans in just a second, and you will see it is not that easy to make it. But anyhow, Frolov tried to patent it in Russia, and he already got his patent. But they had a court case, and Moller won, and so they canceled the patent, and so Moller has kind of won with his strategy, and his point was it's his idea, and so in court he won. So I don't know Frolov's story firsthand, but I know Nicholas Moller, and what is exactly true I don't know, but the court, at least, they gave the right to Moller, And so he has the tubes, and we can download the plans, and no one can claim it as a patent, which is good for all of us. So if anyone wants to build this, he can go ahead and do it. So here we see now how it's principally made inside, and you will see there's a 0.1 atmosphere of hydrogen so hydrogen molecules inside, and then you have here tungsten filaments which are welded to these structures, and they are welded at the cross points. Then you have a certain geometry here, and especially like the distance between the filaments and the outside wall is very important for the way this tube will work. And then here you have like a double shell with where water flows in, and you have you cool by water, but you also take the heat energy out with this cooling water. So so basically what will happen is that you then apply a voltage, and you don't apply DC voltage, but you apply a AC or pulsed voltage to the top and the bottom of the filaments, and they heat up, and then at the filaments, which you have to heat them up above this 1800 Kelvin, so let's say to about 3000, and then the hydrogen dissociates. It goes from the filaments to the walls. The walls are cool, it recombines, and with this process you're using what Langmuir has found, is that there's an energy anomaly in hydrogen. So if you dissociate and you recombine it, you get some excess energy. Here we look again at some of these plans, and these plans, like I say, are available on the internet with all the manufacturing details, about 7 of these pictures, and they also give you, they are lucky for you in English, so they hear all the details, how to make them. Part of the tricks how to make it is it has to be gas tight, and it has to have a little bit of special material, because hydrogen, many metals are like doors for the hydrogen. It can flow out very easily because hydrogen is very small, and many metals can absorb a lot of hydrogen, but they also let it go through. So you have to have something which is hydrogen tight. That makes it special. And well, the rest is mainly manufacturing in such a way that the distances are precise, and that the heat, so it can withstand the heat. And so especially the tungsten filaments and how to weld them, that is very important. And yeah, and the rest is that you have to combine metals with other non-conducting materials, because at the end you want to apply a voltage to the and let the current flow through the tungsten filaments, so they heat up. So that makes it a little bit difficult, but not too difficult. So if someone wants to make them, they can go ahead and do it. But if you look at the details, you will see it's not that easy to make them. Here we see a picture which you can also find in the internet, and that is how Jean-Louis Nodin is measuring this. Here you see the tube. There is water pipes going in and out, and here you have on the bottom the connections for the electricity input. So in this case he is pulsing. So he has these scopes here to really measure the incoming power in the right way. And on this side, he is measuring the flow of the water and the temperature. So the experiment is pretty simple. You have to measure the incoming electrical input correctly, and you have to measure the outgoing temperature difference between the inflowing and outflowing water and the amount of water, and then you can calculate the outgoing power. So here you see this is the other tube. So these tubes, there are two tubes, and the other one is built into this structure, which is originally from Russia, and it's basically the same as you saw on this picture, only that here everything is kind of built in or permanently built. So here you have the flow meter and the temperature meter. Here you have a temperature sensor, and what you can a little bit see here is the electrical input, and here is a car radiator and a pump as a cooling system. So here you have a drawing, a principal drawing of what is happening here. Here's a vacuum tube. Here is the water system, flowing in, flowing out, a pump, a cooler, and a water tank, and most important here the temperature sensors, and here the water flow meter. And on the other hand, you can have different inputs. In this sense, here you have the power from the grid, and you have a very simple rectifier, power rectifier, and step down transformer, and this is just for safety. So there are various ways of running this tube. We will see a few graphs in just here. So here you see the electrical input, and here you see the electrical output, and this is the flow meter and the temperature difference. So, and in this graph, which is like an overall graph, all these points are measurements that Nordin conducted, and here you see that if you run with more power, you get even better efficiencies. So this is also what we have observed, like a factor of 2, and if you use various pulse modes, then apparently you can get better efficiencies than factor 2. So here is a graph which explains how Jean-Louis and Nicolas Moller think it works. So they say you have, if you have DC, what you can barely see is that there's, this line, DC mode. If you have DC, you have this filament temperature. But if you're using the AC, you can get, for short periods, higher temperatures in the filament. And you need these high temperatures because only at these regions you have enough dissociation of hydrogen to make this effect work. So, and that's also what Jean-Louis shows, that in the DC mode, the tube does not show excess energy, but in the pulsed mode and in this AC mode, it does. So, another important incidence is here you see a visitor in the GIFnet. So in, I think it was March 2005, Kofi Anand visited the GIFnet and looked at the technology, and here Nicolas Moller explains to him similarly what I explained to you. This is Jean-Louis Nordin, who's also present. This is close to Paris in a small town with a very big castle, very nice town. And here you see what Kofi Anand wrote to the GIFnet. So I know in some parts of the US, Kofi Annan is not so popular, but at least he's a very prominent person, and it's good if people of his caliber come see technologies like this, and the UN is for the world at least institution, and so he highly recommends that along these lines research should be conducted, and he wishes GIFNet all the best, that they can provide more energy for a better world. Little something interesting here on this TeslaTech conference, why Nicolas Möller was in contact with Kofi Annan, and that is Nicolas worked very hard and quite a few years to get the Tesla archives into there's the UNESCO World Heritage. You might have heard about that. Like there's many sites and many cities with that are like a World Heritage. It's a list of objects, cities, and things, and the UNESCO has it, and it's like a prestigious thing to be in there. And so he worked a long time that all the Tesla material, which is all the files and everything, that they become a World Heritage. And for that reason, he was also in contact with Kofi Annan for quite some time and got into personal contact with him. And that's why Kofi went to, when he was in Paris, to his lab and saw it and everything. And another good thing about this UNESCO thing is that shortly all the files, all the work of Tesla should be on the internet. That like the government of, I think it's Croatia, where that is located, they have donated money so that all the files could be scanned and put on the internet. That was part of this UNESCO deal. You see, usually the UNESCO will say, okay, you come into this list, but you have to do this and that, otherwise you don't get into this list, like not destroy it and the various things to it. So I think that's interesting here. Here you see some, this group went to Paris, so this is in some hotel in Paris. We're here talking to Nicolas Möller. This is Andreas Mantai, which I'm working with for many, many years. He's like the co-founder of the Berlin Institute, and so most of my way in the new energies I have gone together with him. This is Professor Gruber. He was the president of the German Space Power Association before me, and this is a co-worker of Mr. Meyer, who was here 2 years ago. So this group went to Paris to look at this technology and to see firsthand if something is really, if it's true or not. So it's like a good day's drive, so it's not that far. So here you see in this building there is the GIFNet in Paris. Here you see some of the group. And well, inside here we are standing in front of this, of the Russian construction, I would say. And this is a step-down transformer. This is Jean-Louis Naudin. And this is our group. And so it takes about half a day to test run this, because it has to get started and all the temperatures have to kind of get level before your measurements are good. So we did this in the morning, and we checked a few things, because like beforehand there was a lot of discussion among us and other people, like what to look for, and especially the measurement of the input voltage was much discussed in the emails. Like we have heard from Mr. Fiala last year how tricky it can be, and like with the angle between the input voltage and current and so forth. And so we checked all that, but then on the way home, all of a sudden I thought, oh, one thing we didn't check, and that was this flow meter, you know, because like we saw the factor 2 in the excess heat. So, but we made many things we made sure of, but one thing we didn't check, which actually would have been pretty much impossible because we would have to force them to kind of dismantle it and then check if the flow meter really shows the right flow, which you can easily do by putting a few buckets and a few objects where you know exactly how much fits in. So that we didn't do, so that's like the little question mark which I have to pass on. But Jean-Louis, we talked to him about it, and he has done the same experiment with his own flow meter, so he was quite confident that that's not a problem. By the way, he showed us another of his experiments, and he, in collaboration with a Japanese professor, he's doing a certain type of cold fusion, and he's also particularly interested in the excess heat coming from it, and he did the experiment for us. It also took a few hours, and it also showed some excess energy. Also a factor 2 or 3, I think 2.5 it was. So at this point, hello? John? Okay, excuse me. No, okay. It was planned to go over to the oh, now I think we have to. Kind of lost here. No, I'm not finished. Can you help me here? Sorry to interrupt you. It's time for the internet.
Anyway, what do you got there? Just keep going down.
Because I wanted to show you the internet side a little bit, so unfortunately I couldn't do it alone.
Yeah, let me go the other way.
You just have to get it on the screen now. Okay, this is the GIFnet side. So maybe start it fresh. Can you start it, restart it?
Oh, from the start?
Yeah?
Okay.
Yeah, just press that. So actually this is the sign of GIFnet, and Nicholas explained to me exactly what every arrow means. I forgot, can't tell you anymore, but it was 1.5 years ago. But there's a lot of meaning in this, in this graph.
Shh, we won't tell anybody.
Okay, I just wanted to show you that if you want to learn more about this technology, you have to go here to projects. And then like,
Research
no, projects.
projects.
Okay, so you see some old favorites like the Tesla turbine and other things that Jean-Louis is also working on. And here, yeah. And here you also find more about these cold fusion things he's doing. And if you press here here you see the tube. Here read more. And then you'll come to this page. And if you scroll down just a little bit more, you will see many test runs and videos and data. And so that's one very good thing about Jean-Louis. He gets everything on the internet very quickly. Okay, so let me go back to the presentation. How are we doing this time?
Yeah, I think we do. Oops.
Yeah, that's okay. Just
Where?
yeah, I think here. Yeah. I can also go like this.
Okay,
Wait,
yeah, you can just, seems to be fine.
don't worry. Yeah. Okay, so here we are with the what we just seen on the GIFnet. So if you want to know anything more about the developments on this project, you can go here. You can also get the plans for which you've seen there. So, okay, so let me go through a few things. I promised you to tell you a little bit about how this all can work, and so I'll tell you a little bit about the 0-point energy, not too much because time is running short, and last year I gave a full-size presentation on the 0-point energy. It's my special interest from many years, and for those who don't know anything about it, it is basically some energy that comes from the quantum mechanical concepts, and that teaches us that in all space there is a lot of energy. So here we have like a system. So in in classical, the system can go to 0, but in quantum mechanics, you still have this amount here, the h-half, and that is called the 0-point energy. And similarly to these sort of systems, if you have any sort of space, there could be electromagnetic resonances inside this space, and also these resonances, they never deplete fully of energy. They always have some left, and that is called the 0-point energy. So if you sum up all the possible frequencies that could be in such a space, then you have to use this formula, and this is the energy per mode, and this is the density of modes in this area, and then you get to this formula, and you will see here that it's by the frequency to the cube. So the smaller the frequency, the higher the frequency, the smaller the wavelengths, more and more energy per mode is present. And so if you have any space, the amount of energy in it is determined very much by the higher frequencies. Well, I'm just giving you it in a very small nutshell. If you want to learn more about 0-point energy, it's not that easy, because either you go into very heavy quantum field theory stuff, or you pretty much stay on a level like this. Here are some artist presentation on this side. If you go, like, each time you go into a small area, then at the end you will see it's not that flat, but there's a lot of things happening. And here, these are also called virtual particles, which means that energy comes and goes. And so the artist made this picture of this kind of vibrant space. So then we also come to things like a Carcinoma Effect, where we see that by using these metal plates, these red areas are metal plates, you can kind of, in between, there's an area where some of the frequencies are distinguished, they are not present. So you have a difference in energy, which results in a pressure, in a force on these metals. And with this sort of geometry, you can actually model space and get areas where there's more and where there's less 0-point energy, and therefore you can convert this random 0-point energy into something with a macroscopic, with a force that has a direction which which can be converted into energy. And so this sort of idea is very important, and this is being proven, and also there's a lot of recent and current experimental work going on in the physics community on this effect, especially in the nanophysics. It is quite important at this point. So here's another drawing where you see that in between the plates, certain wavelengths which are too long, they can't exist. And because they don't exist, they don't go into the formula, and that's why you have the difference. Here is something which comes out of very current research, is that what we've seen here is like it's a principle, while this is a correction factor if you go into actual material. Then what happens is you don't have something like an ideal metal or ideal mirror, which really reflects all photons. But you see most metals, here is copper and silver, they don't reflect photons with wavelengths of, let's say here, less than 300 micrometer, 300 nanometer, 100 nanometers. So this is like, here is a visible light spectrum. So they just, the silver mirrors are quite good. They still reflect the visible light, but just after it kind of breaks down. Basically that means the photon doesn't see a collective electron sea anymore and is not reflected. It will only see more single electrons, and some are reflected, but very, very few. And in this way, if you take that into account, then also the Carcinoma effect, this effect on depleting modes is not there anymore. So if we want to think of how to use the Carcinoma effect and certain things, then metals, they become useless for the very high frequencies, and that means that we cannot really use it. So, but what happens now here in the with the hydrogen atoms, it's quite interesting, and here we come to the physical explanation of it, is that if you have a hydrogen atom, a molecule, it's about 1 nanometer large, and here it's this is atomic hydrogen, much smaller already. But if you take away the last electron of the hydrogen atom, then you are left with just a proton. And there is really a very large difference in size. So this is a femtometer, which is like minus 15, while this is a nanometer, which is only minus 9. So you have roughly 5 orders of magnitude, difference. So that is quite a lot, and that's a lot of energy. If you would have the full energy, it will be around a GeV per atom. So that will give, if you use something like a Carcinoma effect between this and that, you have energies which are like in a hydrogen bomb. So, but let's say the electron is not an effective shield, so we kind of grade down, then still the amounts of energy we can get by hydrogen based principles will be very large because of this difference. All the other chemicals, they don't do this. If you take away a few electrons, they get a little bit smaller, but there's not this big of a difference. So I think this is why the hydrogen atom is a very special atom, and I think in these tubes you will have some dissociation, you will have some, this will also play a major role in this tube. So what's next? Well, I know I've spoken with Nicolas Moller just before leaving for this conference, and he is, excuse me, he is making another batch of about 300 tubes. And these tubes are made out of glass, and they are much, much cheaper than these original ones. And he's currently working on to make the tubes so they're very cheap they are easy to use. And another thing that what I would like to do is make an independent test run so I can control all the parameters and check it carefully. So to be really sure that we really see over unity here. And well, these tubes, I think he has a little bit of a problem because when I spoke to him last year, October, he said, okay, you can have one in a couple of weeks. And I spoke with him now and he said, okay, you can have one in 1.5 months. So, so I think that there's some little bit of a problem with the material or something. He was also mentioning some companies that got into, that broke down and others he had to buy and so forth. But so I don't know exactly what is the problem there, but they should come out soon. I don't know what he wants to do with his 300 once he has them, but it's his next aim to really produce them. He's looking for, and I think he has already bought a company to make tubes, and so he thinks of supplying. This first batch with his 300 will be still, I think, samples, and but if they are easy to make, then you might be able to make them yourself. I hope they come out before winter because my gas bill is just too much for heating the house. So I thank you very much for your attention, and I'll be able to take questions now.
Well, we have a few minutes for question and answer. If Mr. Ludwig would like to entertain a few. We're gonna try an interesting another format. How about if you come up to the corner here, just walk over here, and we're just gonna start a line at the base of the stairs here. Who's ever front in line here? I guess somebody's backing up in front of me. I guess they want to be first. And then after that, just return back to your seats, and we'll just pass the mic back, okay? That way we'll have a good idea of how many people are interested. State your name, where you're from, and then your question.
Ted Loader from New Hampshire. Quick question for you, Thorsten. Enjoyed your talk. Have you tried this? Has anybody tried this experiment with deuterium? And would you see, with deuterium? Has anybody tried the experiment with deuterium, and would you see the same kind of effects, more, less, or the same?
Well, this tube is not made to exchange the gas. If you look at it, you will see it's sealed. It's made the way it is, and that's the way it runs. So I have started to go in that direction, but I haven't managed to go even that far.
Yeah, no, I was just thinking, you know, instead of filling it with standard hydrogen, monatomic hydrogen or H2 monatomic, fill it with deuterium gas and see whether the same heat process or the breaking
it would be very interesting.
It would be very interesting, yes.
Yeah, definitely. I think
let us know what happened next year.
It will be very much the same. That's what I think. It will be very much the same. But we'll see.
Yeah, good.
I'm Steve Kaplan, New Energy Movement, and I wanted to find out what the strategy is. This is in a fairly early stage of research and development, I take it, but what's the strategy for bringing it out to the public?
Well, see, his strategy is that he talks about it, he invites people and so forth, but we are trying to be very close with the things, and like I said, with these next generation of tubes, we are asking for them, and they're not coming that easy, you know. So he has very open strategy. Okay, so he's trying to make more tubes naturally, to make it more simple, make it easy, and then you can have plans. And he thinks that he can produce them and, of course, sell them. And he's not wanting to sell them to make like exclusively like this, but it's like light bulbs, you know. You can buy them from many companies, and they all make their living because you don't want to make the light bulb yourself at home, you know.
So basically it's an open source model. He's not trying to go to a company and get them to produce it.
See, he didn't patent it. He is, see, there are two things of conserving or saving your ideas. One is to publish and one is to patent, and he's publishing everything, so.
So conceivably, any number of companies could take that and run with it with production for human use.
Yeah, if anyone wants to go ahead and start doing it, no problem, yeah.
Okay, thanks.
Go ahead, I pretty much have.
Okay, on the Casimir, first of all, my name is David Baxter. I'm from Salt Lake City. And I understand from the late Dr. Robert Forward that that spears of mica can be used to bring the reflection for zero-point energy down to 1 nanometer or less. Any comments on that?
Yeah, I don't really understand how he will do that. Well, that's mica? He
Mica, yeah, the element mica, yeah. Supposedly it's conducting also.
Yeah, well, I'd be surprised to 1 nanometer. That's very, I don't know if anyone has some details on that. It would mean that it should be reflective down to that wavelength, and I'm not sure.
Yeah,
well,
I think
maybe you see, most materials, they reflect something, okay? They hold something, but
mineral,
not too much.
Yeah, I meant
maybe
mineral.
It's a good idea, I don't know.
Okay.
Good afternoon. My name is Ross Barabler from Pagosa Springs, Colorado. In layman's terms, to use a unit like this for heating, radiant heating in a home, what would you imagine the output would be if you ran in water, say at 40 degrees Fahrenheit? What would
you see,
potential output?
On one of the graphs you saw that these that you can, like one kilowatt that was on the graph, you know, like, so maybe it's quite easy to make 1.5 kilowatt in that size. So you have, if it's running, like, let's say on an over unity of 10, you give in 100 watts and you get out a kilowatt like this. So they're simple, small. I think it will be no problem to integrate it into your home system.
So again, what would kind of a temperature would you get out if you put in, say, 40 degrees of water?
Well, that depends very much on the flow of your water. Okay, you can calculate that easily. If you have 1 kilowatt, you want a temperature difference of, let's say, 20, then you will have a small flow.
The slower the flow, the higher the temperature output.
Yeah.
Okay.
Because the energy output should depend on your input electricity and not on the water.
Right. Okay. Thank you.
Are there anyone else? Thorsten Ludwig, Dr. Thorsten Ludwig, thank you very much.
Yeah.